Alright, so today we'll be doing AS Chemistry Unit 2, and this is a January 2025 past paper. It's the latest past paper that you can find online. Before we begin, I'll tell you a bit about my classes. So my name is Hamad Mohammed, as you can see in the meets, and I've been teaching since 2023. I started with AS Physics, then I began teaching other subjects as well, and I've taught over 40 people, I think, probably. And look, the objective of my classes is to pass down the knowledge that I have, and I use that knowledge to get these A stars, like all 3 A stars in all the subjects I did in A level. So with every single question that we do in the classes, I hope you learn something new that you didn't know before. Oh, he's here. Okay, so as I was saying, with every single question that we do in the classes, my objective is that you learn something new. And I guarantee that these classes are going to help you tremendously in your exam preparation. So you can decide if you want group classes or individual classes. Now, group classes are past paper only classes. But if you want individual classes, then you'll have to discuss it with me, because I can't offer everyone individual classes. Like, it depends on availability and stuff, you know. Okay, so with that being said, let's begin. Question number 1. An alcohol can be attacked by a nucleophile because, so we have 4 options. The CO bond is weak. That is not the reason why an alcohol can be attacked by a nucleophile. Look, you need to understand what a nucleophile is. Okay, a nucleophile is a species that can attack an electron deficient region in a molecule. What do we mean by electron deficient? Electron deficient basically means a positive charge or a deficiency of electrons. Now, alcohols can be attacked by nucleophiles because they do have an electron deficient region. And where is that electron deficient region? It is the CO bond. Now, oxygen is very electronegative. So in the CO bond, most of the electrons are going to be attracted towards oxygen. So oxygen is going to have a negative dipole. At the same time, carbon is going to have a positive dipole. And as you can see, this positive dipole is what we call the electron deficient region. So alcohols can be attacked by nucleophiles because the CO bond is polar. This is what we call a polar bond, in which one atom it has a negative pole, a negative dipole, and the other atom has a positive dipole. So that is why nucleophiles attack alcohols. So option B is the correct option. You can look at the marker scheme as well. Yes, option B is the correct option. Okay. Let's move on to question number 2. Also, if you have any doubt at any point, feel free to ask. Okay. Question 2. A student sketched a graph of the temperature of the decomposition of some of the group 2 nitrates against the metal's atomic number. So we have temperature in Kelvin on the y-axis, and we have the atomic number on the x-axis. It is very important that whenever you have a graph, you look at the axes as well. It's very important to look at the units, because a lot of the times the question tries to confuse you with the units. So in this question, they're asking to use the graph to estimate the temperature in Celsius. So again, in Celsius. If you don't read the question properly, you'll get it wrong. So use the graph to estimate the temperature in Celsius at which calcium nitrate decomposes. Okay. So now, what is the atomic number of nitrogen? Sorry, of calcium, not nitrogen. Look at the periodic table. Yeah, it's 20. Yes, exactly. It's 20. So we're going to look at the x-axis. Where is 20 located? It is located right here. Now read the graph, look at the temperature. You can see that calcium nitrate decomposes at about 1, 2, 3 at 860 Kelvin. Now we have to convert this into Celsius. If you didn't read the question properly, you would have chosen option C, which is wrong. So how do we convert Kelvin to Celsius? Do you know?
You subtract 273.
Exactly. You subtract 273, so 860 minus 273, and that should give you about 587 Celsius. So option A is the correct option. So,
So do
yeah.
we take the calcium as the reference, not the nitrogen?
Yes, because it says in the question that the graph is about the temperature against the metal's atomic number.
Okay.
Yeah. So the atomic number is about the metal, not the nitrate or nitrogen. Okay, question 3 then. 20 centimeter cubed of a saturated solution of barium nitrate at 80 degrees Celsius was cooled to 20 degrees Celsius. 9.32 grams of crystals were precipitated. The solubility of barium nitrate is 3.74 grams per 100 grams of water at 20 degrees Celsius. What is the solubility of barium nitrate at 80 degrees Celsius in grams per 100 grams of water? So, you have to know that in general, if you increase the temperature, the solubility of a salt is also going to increase. So at higher temperatures, you can dissolve more salt into water. The same thing's happening here. At 80 degrees Celsius, the solubility of barium nitrate was much higher than at 20 degrees Celsius. So when the solution was cooled down to 20 degrees Celsius, the crystals, 9.32 grams of crystals, were precipitated. These crystals were originally dissolved, but because the solubility decreased, they could no longer be dissolved into the solution. That's why they precipitated. Now, we know that at 20 degrees Celsius, the solubility is 3.74 grams per 100 grams of water. So in 100 grams of water, the maximum amount of barium nitrate you can have is 3.74 grams. How much water do we have in the question? So we have 20 centimeter cubed of the liquid, of the solution basically. Do you know the density of water?
It's 1 gram per centimeter.
1 gram per centimeter cubed, exactly. So here we have 20 grams of water. So how much barium nitrate do we have at 20 degrees Celsius? We can use direct proportion here. The mass comes here, and let's say that the mass of the water comes here. So at 100 grams of water, we have 3.74 grams of barium nitrate. At 20 grams of water, we have X grams of barium nitrate. Cross multiply, X equals 3.74 into 20 divided by 100. And now you're going to use your calculator. How much mass of barium nitrate do you have at 20 degrees Celsius? Let me use my calculator. You should get about, hold on, I'm using a digital one. Okay, you should get
We get less, like 0.748.
0.748. Yeah, 0.748. Okay. So we have 0.748 grams at 20 degrees Celsius. Now, how much barium nitrate did we have at 80 degrees Celsius? We're going to add this with 9.32. That's going to give us the mass of barium nitrate at 80 degrees Celsius. You understand? So look, when we cooled down the solution from 80 to 20, right? 9.32 grams of crystals were precipitated. These were originally dissolved into the solution at 80 degrees Celsius. Now, after these were precipitated out, what did we have left? We had 0.748 grams left still in the solution. So that means that 0.748 plus 9.32, which is the crystals, these are the crystals. This total mass was originally in the solution at 80 degrees Celsius. Okay? So that's why when we add these together, we get the total mass at 80 degrees Celsius. So we're going to use the calculator again to find the total mass. and we get 10.068 grams. So that is the amount of barium nitrate we have at 80 degrees Celsius in 20 grams of water. Okay? So, finally, how do we get the concentration, the solubility per 100 grams of water? So 10.068 divided by 20 grams of water, because this is how much barium nitrate we have in 20 grams of water, and we're going to multiply this with 100. And so we get hold on, 10.068 divided by 20 multiplied with 100. We get 50.34 grams per 100 grams of water, which is around 50.3. So the correct option is option D. Yes.
When you divide by 20, why did we divide by 20?
So again, we're using the concept of proportion. If you got confused by this, that's fine. We'll just do it this way, cross multiplication. So we're going to write the mass of barium nitrate here and the mass of water here. Okay. Now we know that in 20 grams of water at 80 degrees Celsius, we have 10.068 grams of barium nitrate, right?
Yeah.
So how much are we going to have in 100 grams of water? Let's say it's X. Now, because it's direct proportion, we're going to cross multiply. So X into 20 equals 100 into 10.068. Change the subject, bring 20 to this side. So X equals 100 into 10.068 divided by 20. And that's going to give you the same answer as 50.34. So that's fine?
Yeah.
Okay. Then let's do question 5. Which order is correct for the solubilities of group 2 sulfates? So again, this is something that is basically explained in detail in the textbooks. What'd you say?
Skip question.
Oh, I skipped question 4? Oh yeah. Sorry. Okay, so what is the flame color produced by strontium ions? Okay, this is just memorization. Nothing to explain here. The answer is red, 4B. You know the colors of transition metal ions, right?
Yeah.
Yeah, just memorize that. That's it. Okay, question 5. Which order is correct for the solubilities of group 2 sulfates? Now in the Edexcel textbook, this is explained in detail, the solubility of group 2 sulfates. The solubility of group 2 sulfates you should know, and let me just write this down by clearing up all of this messy working. The solubility of group 2 sulfates decreases down the group. Someone said something in the chat. Yes, you are correct. It decreases down the group, exactly. So, let's look at the periodic table. So we're concerned with the first three, barium, strontium, and magnesium. Okay. So where is this? Yeah, this is barium, this is strontium, and calcium. Okay. So it decreases down the group, right? Meaning calcium is going to come first. It's going to have the highest solubility, calcium sulfate. Then strontium sulfate is going to be less soluble than calcium sulfate. And then finally, at the end, we have barium sulfate, which is the least soluble. In fact, you might know that we use barium in some tests, and the precipitate of barium sulfate, exactly, it's used in the test for sulfuric ions. When you use barium, it forms a precipitate of barium sulfate because barium sulfate is insoluble. So our answer, hence, is going to be option D. That is going to be the correct answer. Yes. Okay, then let's move on to question 6. Which is the best solvent for chloroethane? So we have ethanol, hexane, hydrochloric acid, and water. Now, in solubility, you have to, yes,
Oh, I just said I think it's
B. Okay,
Yeah.
B is not correct.
Not correct. Okay.
Not correct. Because you have to know a concept called like dissolves like. Basically, a similar substance will dissolve a similar substance. So if you have a polar compound, it will likely be dissolved in another polar compound, a polar solvent. If you have a non-polar solvent, it will likely be dissolved in another non-polar solvent. Now here, hexane is a non-polar solvent, but chloroethane is a polar substance, right? Because this is the carbon, and this is chlorine. As we know, chlorine is pretty electronegative. It's in group 7, so it's going to be a very electronegative. Hence, this is going to be a polar bond. The CCl bond is going to be polar. This is going to have a negative dipole. This is going to have a positive dipole. So, the correct answer is actually option A, ethanol, because ethanol is also polar. Now you might think, okay, water is also polar, right? So why doesn't it dissolve in water? The thing is, water is actually very polar. It's much more polar than chloroethane, and because of that, it also forms hydrogen bonds. So these hydrogen bonds are hard to break. These are very hard to break. That's why chloroethane doesn't have enough power, basically. You can think of it like that. It doesn't have enough power to break these hydrogen bonds and dissolve in water. That's why the correct option is option A.
And C,
Uh,
I would think HCl would be polar.
you think that HCl?
Would be polar because chlorine. I think chlorine's
Yes,
electronegative.
it will be polar, exactly. But then hydrochloric acid is in water. It's a solution, right? So it's still inside water. You're still gonna have a lot of water molecules in hydrochloric acid. That's why it won't dissolve in hydrochloric acid either. I mean, if you have concentrated hydrochloric acid, then I think it'll dissolve. I'm not sure on that, but as far as dilute hydrochloric acid goes, haloalkanes just don't dissolve there in hydrochloric acid.
So the reason is because it's in water.
Yes, and also hydrochloric acid is not in water. It's not HCl bonded. These two things dissociate. The hydrogen and the chloride ion, like, what do you have? You have a hydrogen ion and you have a chloride ion. These are not bonded together, so it doesn't form a polar sort of polar bond, because they're not even bonded together.
Okay.
Yeah, and then obviously you have water as well. So because of these reasons, it doesn't dissolve in hydrochloric acid. So we can generalize this, and we can say that haloalkanes best dissolve in alcohols. And this is what you can learn from this question. Okay, let's move on. Question 7. Let's check the mark scheme as well. Yeah, ethanol is the correct answer. Okay, question 7. The molecular masses and boiling temperatures of hydrogen fluoride, hydrogen chloride, and hydrogen iodide are shown. So what is the best estimate for the boiling temperature of hydrogen bromide? Now this is a textbook question. It's explained there directly in the textbook. You don't even have to think about this. You just have to know one thing. When we talk about these hydrogen halides, right? They follow a very distinctive pattern. Hold on, someone's joining. Okay. Uh, yes, we are doing Jan 2025 Chemistry Unit 2. Okay, so as I was saying in question 7, hydrogen halides follow a very distinctive pattern when it comes to their boiling temperatures. If you were to plot a graph, let's say a dot plot. So we'd have hydrogen fluoride here, then we'd have hydrogen chloride, then we'd have hydrogen bromide, then we'd have hydrogen iodide here, and this, let's say this is their boiling temperature. Hydrogen fluoride is going to have the highest boiling temperature out of all the hydrogen halides. Then after hydrogen fluoride, hydrogen chloride is going to have the lowest boiling point out of all the hydrogen halides. Then after that, the boiling point steadily increases. So hydrogen bromide has a higher boiling point than hydrogen fluoride, and hydrogen iodide has a higher boiling point than hydrogen bromide. So you can learn this graph or screenshot this if you want. So this pattern is what you have to know. Because of this, we know that hydrogen bromide is going to have a higher boiling temperature than hydrogen chloride, but a lower boiling temperature than hydrogen iodide. So it's going to be in between minus 85 and minus 35.1. The only option hence is minus 67 degrees Celsius. Option C. Yes, I'll explain the reason as well. The reason behind the trend is, okay, we know that if you have stronger intermolecular forces, you're going to have a higher boiling temperature, right? So if you have more London forces, if you have stronger London forces, you're going to have a higher BP. If you have permanent dipole forces, you're going to have a higher BP. If you have more hydrogen bonds, you're going to have a higher BP. Now, hydrogen bonds, and actually let me write this down as well. Hydrogen bonds are the strongest intermolecular forces out of all the three intermolecular forces. Now, the only hydrogen halide that forms hydrogen bonds is hydrogen fluoride. Hydrogen fluoride is the only hydrogen halide that forms hydrogen bonds. No other hydrogen halide forms hydrogen bonds. And because hydrogen bonds are the strongest, that's why hydrogen fluoride has the highest boiling point. Okay? Now, beyond that, what about the rest of the hydrogen halides? HCl, HBr, and HI. For them, there are no hydrogen bonds. So what are the intermolecular forces that they have? They have London forces. You know what London forces are, right? They have London forces and they have permanent dipole forces. Guys, if anyone else could also contribute to the lesson, that'd be appreciated because I'm teaching all of you here. Okay. They have London forces and, permanent dipole forces. Now we know that London forces become stronger as the mass of the compound or the molecule increases. Right? Bromine has, and you can see this in the table as well. Bromine, HBr, okay, you can't say HBr, but HI has more mass than HCl, and HBr has more mass than HCl, but less mass than HI. So HCl is going to have the weakest London forces, HBr is going to have a bit stronger London forces, and HI is going to have the strongest London forces. Because of this, for HCl, HBr, and HI, the boiling temperature steadily increases as you go down the group. Okay? So that's why this trend is followed. So is that clear?
Yes, it's clear.
And you can screenshot this writing as well if you want. Okay. Then part B. Let me clear this up a little bit. Why does HF not fit the pattern of the boiling temperature of the other hydrogen halides? So again, this question can be answered with this information. So what do you think is the correct option? A is the correct option, exactly. It forms hydrogen bonds. If hydrogen halide did not, if hydrogen fluoride did not form any hydrogen bonds, then it would have the smallest the lowest boiling temperature. But because it does form hydrogen bonds, that's why it has the highest boiling temperature. And yeah, option A is the correct option. Okay, let's move on. Question 8. An experiment measuring the concentration of a reactant over time produced the graph shown. What is the approximate value of the initial rate of reaction? Now, do you know how to find the rate of reaction from a concentration time graph?
I used to take like 2 points generally and then just find like changing y by changing x to find the general concentration. I mean the general rate. I don't know.
You can't do that here because this is a curved graph. You can do that if you have a straight line graph, because in a straight line graph the gradient is constant. But because this is a curved graph, you won't be able to do that. What you would need to do is you would need to draw a tangent. Now, of course, I can't use a ruler here digitally, but a tangent is basically, okay, it's a line, straight line that touches the curve at only one point. So it's going to be like a bit like this. Okay. So when you draw this tangent, now you have a straight line, right? And keep in mind, you have to draw the tangent at the start of the graph because they're asking for the initial rate of reaction. So you draw the tangent and then you find the gradient of this tangent, of this straight line. Just like you said, you take 2 points, you find the change in concentration, change in time, and divide them, and that's how you get the rate of reaction. So do the same thing with the tangent. Now, I don't have a ruler, so this is not going to be accurate. So when you do the same thing with this, you find the gradient, you should get the answer, you should get option A as the correct answer. Okay?
So we just take the gradient of the tangent.
Exactly. So we can write that as well. This is something that we learned from this question. We learned that to find the rate of reaction from a concentration time graph, you should draw a tangent at the point where you want to find the rate. So here we wanted to find the rate at the initial point. That's why we took the tangent at the initial point. Now another thing which is not assessed in this question, to find the average rate of reaction. Okay, the average rate of reaction of the entire reaction. The formula is 1 divided by the total time taken. This is something that is worth knowing as well. So here, if you wanted to find the average rate of reaction, what is the total time taken? It's about, let's say 400, right? So the average rate is going to be 1 divided by 400. Okay. Then part B, what are the units for the rate of reaction? So do you know the units of the rate of reaction?
Is it B?
Mole per dm cubed by seconds? Yes, it is B. That is the correct option. Option B, yes. Sorry for the messy writing. Yeah. What about Naluni? I hope that I'm pronouncing that correctly. Is everything clear so far? You can use the chat as well if you want. Okay. Yes, I didn't check the chat. You said tangent from 0? Correct. That is correct. Okay, let's move on. Question number 9. Concentrated sulfuric acid reacts with sodium iodide. What is one role of the sulfuric acid? Okay, so this is something that is there in the textbook, and you have to check the textbook, and you have to learn the concentrations, sorry, not concentrations, reactions of sodium halides with concentrated sulfuric acid. So these are important reactions. You have to memorize them, unfortunately. This is why I hated chemistry in A levels, because there was too much to memorize. Yeah. You have to memorize the three reactions, right? So the reaction for sodium chloride, then the reaction for sodium iodide, then the reaction for sodium bromide as well. Now the thing that makes it even harder is that sodium bromide and sodium iodide have further reactions as well, which you have to memorize. So in total, you have to memorize about 6 reactions in total from this. Okay, so you're going to learn that concentrated sulfuric acid acts as the oxidizing agent in this reaction, and the sodium halide acts as, or the halide acts as the reducing agent. In these reactions, the sulfuric acid acts as the oxidizing agent, and the halide acts as the reducing agent. This is something that is very important. You have to write this down or screenshot this. Okay. Now, for A2 paper, yes, I will be taking a class on A2 tomorrow as well. I have sent you the schedule. You can check the schedule for the timings. What is your Reddit username, by the way? Just so I can see, like, mark the attendance basically. Upper ship 123. Okay, I didn't see you in my DMs. Okay, let me write that down. Upper ship 123. Okay, I'll contact you as well. For chemistry A2 is going to be the same link. Okay, so as I was saying, sulfuric acid acts as the oxidizing agent and halide acts as a reducing agent. Now, what is the reason for this? The reason is that halide ions are very good reducing agents. When something is being reduced or oxidized, what does it mean? Oxidized means gain of loss of electrons, right?
Yes.
Yes. And reduced means gain of electrons. So when something is a reducing agent, do you think that it's getting oxidized or reduced?
It's going to get oxidized.
It is
Losing oxygen.
exactly. It is going to get oxidized. A reducing agent gets oxidized. The reason why halide ions get oxidized very easily is because they have a tendency to lose electrons. Why? Because look, in a halide ion, like as you go down the group from chloride to bromide to iodide, the atomic radius increases, right?
Yes.
The atomic radius increases. And also, the number of electron shells between the valence shell and the nucleus also increases, right? This is what we call shielding. Do you know what shielding is?
Yeah.
This is what we
It's
call
like
shielding.
when those kind of like weaken, they kind of like repel each other, so they weaken that force between the nucleus and the outer shell. Like no, actually, it repels the outer shell electrons more.
Exactly. It increases repulsion. And what does that do? It reduces the power of the force, of the nuclear force on the electrons, right? On the outer shell.
Yeah.
What that does is that it in turn reduces the electronegativity. So as you go down the group, the halide ions, they're not able to hold their outer electrons easily because the force is so weakened by shielding and by the distance, right? And because the force is weakened, the reducing power increases because they get oxidized more and more easily. They lose electrons more and more easily. So they become better reducing agents as you go down the group. Okay? So, so that's why hydrogen chloride, or like a chloride ion, is an okay-ish reducing agent. A bromide ion is a better reducing agent, and an iodide ion is the best reducing agent. I think I should have wrote that down. Let me just write that down quickly. as you go down the group, because all of this, I know it's not related to to the to the question, but it's like important stuff. So as you go down the group, the atomic radius increases, and the shielding also increases. This reduces the power, or the effect, I think is better to say, the effect of the nuclear electrostatic force on the outer shell. This hence reduces negativity. Finally, this means that electrons are lost more easily. Hence, halide ions get oxidized much easier as you go down the group. Okay, that's it. So you can screenshot this as well if you want. Okay. Shall we do question 10 then? Okay. Which equation is not an example of disproportionation? Now, you could look at all the elements, like in option A. You can look at copper and figure out the oxidation state of copper on the left hand side, right hand side, then determine if it's disproportionation or not. That's going to take a lot of time. What you can simply do is you can look at the reaction in which an element is not being repeated twice on the right hand side. What do I mean by this? In option A, you have copper on the left hand side once. On the right hand side, you have copper once and twice. In disproportionation reactions, an element usually it appears twice on the right hand side. Okay? So copper, it appears twice on the right hand side, so we can cut out option A. Then in option B, nitrogen appears twice on the right hand side, so and here, so we can cut that out. Option C, chlorine, yes, appears twice on the right hand side, so we can cut this out as well. What about option D? Now here, magnesium appears only once on the left hand side and the right hand side. Same thing for hydrogen, same thing for chlorine. This hence cannot be a disproportionation reaction. In a disproportionation reaction, an element always appears twice on the right hand side. Because no element is appearing twice on the right hand side, option D cannot be a disproportionation reaction. That's why option D is the correct option. Now, if in all the options an element was appearing twice on the right hand side in all of the options, then you'd have to individually look at the oxidation states, which is unfortunate because that takes a lot of time. But if you have a question like this, then you're lucky because it's an easy answer. You can just directly look at the equation and that's it. So what did you learn from this question? You learned that when any element does not appear twice on the right hand side, it cannot be a disproportionation reaction. Okay, is that clear?
Yes, it's clear.
Okay, let's move on to question 11. Which is a displacement reaction that results in a visible color change in solution? Okay, now if you don't know the color changes, that's fine. I don't either. This is a trick question. You don't have to know the color changes. In this question, there's only one reaction that is feasible, that is possible. All other reactions are not possible. So the reaction that is possible, that can physically happen, that is obviously going to be the correct option. Right? So which reaction is going to be possible? And now here, C, iodine, bromine. Yes, you're correct. Option C is the correct option. Option C is the only correct option because that is the only reaction that is possible. But why? How did you get C?
And iodine.
Exactly. Bromine is more reactive than iodine. Guys, these options are displacement reactions. In a displacement reaction, the, the less reactive element gets displaced by a more reactive element. So if you have a more reactive element being displaced by a less reactive element, that is impossible. In option A, chlorine is being displaced by astatine. Astatine is not as reactive as chlorine, so this is impossible. Option B, same thing. Bromine is being displaced by iodine, but bromine is more reactive, so this is also impossible. That's why the correct option is option C. Same thing for option D. You can cut that out as well. Okay. So let's move on. Question 12. A sample of 25 centimeter cubed of 0.205 mole per dm cubed sulfuric acid was titrated with sodium hydroxide solution. The titer obtained was 14.6 centimeter cubed. What is the concentration of the sodium hydroxide solution? Okay, can anyone tell me what is the concentration of hydrogen ions in this sulfuric acid solution?
Could you repeat the question?
What is the concentration of hydrogen ions in the sulfuric acid solution?
No idea.
Okay.
Can you give?
Yes?
No, I'm saying the other student answer. They said 2
Oh,
times 0.20.
exactly. I don't know why when someone says something in the chat, it doesn't give me a notification. But okay. 2 times 0.205, that is correct. But why? Well, we know that sulfuric acid is H2SO4. Okay, H2SO4. This is sulfuric acid. In one molecule of sulfuric acid, you have 2 hydrogen atoms, right? So when you dissolve this in water, when you make a solution of sulfuric acid, for every molecule of H2SO4, it's going to produce 2 hydrogen ions. Okay? So if the concentration of sulfuric acid is 0.205, the concentration of hydrogen ions is going to be twice 0.205. You understand? So we know that the concentration of hydrogen ions is twice 0.205. So 2 into 0.205, that is 0.51. Okay. Now we know the concentration. Let's find out how many hydrogen ions we have in the sulfuric acid solution. So,
I think it's 4.
oh, 4-1, yes, sorry. 4-1. Okay, so we know that the solution, the volume of the solution is 25 centimeter cubed. The concentration is given in mole per dm cubed, so we're going to convert this into dm cubed as well. So 25 divided by 1,000. Okay, and so what is the formula to get the number of moles when you have the concentration and the volume?
You just multiply the 2.
You multiply the two, exactly. So 0.41 multiplied with 25 over 1000, and that gives you, let me use my calculator, 0.41 into 25 divided by 1000. That gives you 0.01025 moles. So we have this many moles, these many moles in the solution. Now, when we titrate the solution with sodium hydroxide, what happens? This is a neutralization reaction, right? So all the hydrogen ions are being neutralized by a hydroxide ion. So if we have 0.01025 moles of hydrogen ions, we must also have 0.01025 moles of hydroxide ions, right? To neutralize the hydrogen ions. Okay. Now, can anyone tell me what is the formula of sodium hydroxide?
It's
NaOH, exactly. If we have 0.01025 moles of hydroxide ions, that must mean that we have 0.01025 moles of sodium hydroxide as well, right? Because each mole of sodium hydroxide produces 1 mole of hydroxide ions. So if you have 100 moles of hydroxide ions, that means that you must have had 100 moles of sodium hydroxide. So the amount of moles of sodium hydroxide that we have is 0.01025. Now we get to the final answer. The titer is 14.6 centimeter cubed. So the volume of sodium hydroxide solution is 14.6 centimeter cubed. Now we have the number of moles, we have the volume. How do we find the concentration? We divide them, right? So moles divided by volume, this is equal to 0.01025 divided by 14.6. And you have to divide 14.6 by 1000 as well, because you have to convert to decimeter cubed. So just use your calculator to get the answer here as well. 14.6 divided by 1000, that equals 0.702 mole per dm cube. Mole per dm cube. So option D is the correct option. Now, yes. Yes.
when we took, we took the concentration of, no, sorry, the moles of H plus ions, I think, to be the same as the OH ion.
Yes.
So, do we just do that because most of them have H plus ions?
No, OH minus ions, an OH minus ion doesn't have an H plus ion. An OH minus ion is an ion by itself. The reason why we take H plus ion, the moles of H plus ions and the moles of OH minus ions as the same, is because for every H plus ion you must have one OH minus ion to neutralize it. So if you have like 1,000 H plus ions, you need to have 1,000 OH minus ions to neutralize the H plus ions, right? If you have 1,000,000 H plus ions, you need to have 1,000,000 OH minus ions to neutralize the H plus ions. That's why the number of moles of OH minus and H plus is always going to be the same in a neutralization reaction. Yeah. Okay. So that's how we get the answer. Okay. Also, this is a repeated type of question. In fact, I think that a lot of these are repeated questions. So if you understand these questions, you should be able to answer many other questions as well. Okay, finally, part B. What is the percentage error in the titer? And the burette is accurate to 0.05 centimeter cubed per reading. Now, that means that 0.05 centimeter cubed is our resolution. It is our resolution. Do you know what the resolution of an instrument is?
Is it half of its reading?
No, the resolution is the smallest possible value that you can measure on the instrument. Like if you have a ruler right in front of you, the smallest possible reading is 1 millimeters, right? So that is the resolution of the ruler. So for the burette, the smallest possible reading that you can have is 0.05 centimeter cubed. Now, have you done physical experiments in school?
No, never.
Okay. Uh, if you have, then you would know how to read.
I have watched like on YouTube video.
Yeah, so you know how they read the burette, right? First they get the initial reading, then they get the final reading. Then they minus it together, right?
Yeah.
Together reading. So in a burette, you're reading the basically you're reading you're taking two readings, right? You're taking two readings, initial value, final value.
Yeah.
So the uncertainty, which is 0.05, the absolute uncertainty. This is okay. Wait, the resolution is actually 0.1, and this is half of the resolution. Okay, I made a mistake there. Sorry. This is half of the resolution. Resolution is 0.1. The absolute uncertainty is half of the resolution. Do you know what the absolute uncertainty is?
I think that's maybe what I said for like when I said it was half.
Yeah, yeah.
But I'm not sure if I don't really understand the significance of it. I know we do it if we like calculate with it, but I don't understand the significance.
Okay, so this is a pretty interesting topic because whenever you use an instrument, the reading that you get, you can never be 100% sure that is the correct reading. There might be microscopic differences, like things that you can't see. Obviously, if you use a ruler, like let's say this is 1 millimeter, right, and this is another millimeter. What if your object is in between these two increments? How do you measure that way? You don't, right? You have an uncertainty basically. You don't know how much this measurement is, this part is. This is your uncertainty. So whatever you measure using any instrument, the actual reading, the actual measurement can always be either below your reading or above your reading. Do you get it?
Yeah.
Yeah. So to measure that uncertainty, to measure the amount of uncertainty that you have, you take half of the resolution. So in a ruler, this is 1 millimeter, this is 2 millimeters. The resolution of a ruler is 1 millimeters, right? You're gonna take half of this as the absolute uncertainty. So 0.5 millimeters is the absolute uncertainty in a ruler. So my point is, in a ruler, if you have the measurement as, let's say, 10 centimeters, right?
Mm-hmm.
Your actual reading could be either 0.5 millimeters above 10 centimeters or 0.5 millimeters below 10 centimeters. You understand?
Yeah.
Okay. So the same thing happens here with the burette. So if you have a burette reading of, let's say, 12 centimeters, the actual reading could be 0.05 centimeters above or 0.05 centimeters below. Okay? Okay. Now, because in a burette you take two readings, and this is something that you have to learn. You have to learn this because this is repeated. In a burette, you take two readings, initial and final. So the absolute uncertainty is added twice. In each reading that you take, you have 0.05 centimeters as the absolute uncertainty. So you have to add this 0.05 plus 0.05. That is your total absolute uncertainty. So we get 0.1. Now, what is the formula for percentage uncertainty or percentage error? Do you know the formula?
Do we just take that like 0.1 over the titer and then multiply that by 100?
Yeah, exactly. You said that we take 0.1 divided by the the total reading and multiply with 100, right?
Yes.
You're correct. That's exactly how we do it. I check the chat right now, and Naluni, you are absolutely correct. So you have a good grasp of the topic. Okay. So 0.1 divided by the titer, 14.6, and you multiply this with 100, and you get. Let me use my calculator. 0.1 divided by 6. So you get 0.684, which is about 0.68%. Hence, that is our answer. So what did we learn from this question? We learned a very important thing. Whenever you talk about a burette, you should know that in a burette you take two readings, final and initial. And so the absolute uncertainty in a burette gets added twice. So the total absolute uncertainty in a burette is twice, like twice 0.05 in this case. Okay?
Okay.
So is that clear?
That's clear.
Then let's move on to question 13. Oh wait, the class is. I guess how many MCQs do we have left? Okay, there's still a couple.
How many?
We have three MCQs left. Let's just finish all the MCQs and then we'll call it a day. Question 14. What is the concentration in mole per dm cubed when 64.5 grams of sodium nitrate is dissolved in water to form 750 centimeter cubed of solution? Okay, this is a very easy question.
But I'm guessing also question 13 will be easy.
Oh, we skipped question 13? Oh, okay, sorry. Calcium carbonate can be heated to produce calcium oxide. What is the atom economy by mass for the formation of calcium oxide? Now, do you know how we calculate atom economy?
I suppose we just give our desired, like our mass or desired product, whatever we want.
Yes.
In this case, I think we're gonna have to take the formula mass of
Okay.
whatever the name is,
Okay.
and then we're just gonna divide it by the total product formula.
By the total mass of the products, and you multiply it with 100. Exactly. So let's just write down the formula, the general formula. Check the chat as well. Okay. So atom economy, mass of desired product divided by total mass of the products. You can also just take the mass of the reactants, because obviously the mass isn't going to change. The mass is conserved. Or products, mass of reactants or products. Let me clear this up a little bit. Okay, and we're going to multiply this with 100. So that's all you have to do. So what is the mass of calcium oxide? You have to go to the periodic table. Yeah, you have to go to the periodic table. Calcium 20 plus oxygen, so 28. Divide that with the mass of calcium carbonate. So 20 plus 24, that is going to be 44 plus 6, so 50. Multiply with 100, and you should get 56%, right? Yep. Okay. Question 14. What is the concentration in mole per dm cubed when 64.5 grams of sodium nitrate is dissolved in water to form 750 centimeter cubed of solution? Okay, very easy question. So obviously, because we want the concentration in mole per dm cubed, we have to find the number of moles of sodium nitrate. So we're going to divide 64.5 by 85, right? And that's going to give us 64.5 by 85. So about 0.7588. It's better to be as accurate as you can. So we have this many moles of sodium nitrate. Then we're going to divide this with the volume of water. So 750 divided by 1000. Again, you have to convert centimeter cubed to dm cubed. So that's why you divide the volume by 1000. Okay, so now you should finally get the answer as 0.75, 1.011 grams. 1.0117, which is about 1.012. So option D is the correct option. We haven't even been looking at the marking scheme, but okay. Yeah, correct. The final, okay, never mind. The penultimate MCQ, question 15. A volume of 10 centimeter cubed magnesium